a Portland Community College mathematics telecourse. A course in arithmetic review, produced at Portland Community College. Quite frequently, when you need the use of the area formulas, you need more than one, and you need to be clever about how you use them. For instance, if we wanted to find the area of this strangely shaped field or lot, perhaps what you would notice first is this particular rectangle. Now, if we first note that this radius is the same even if it's measured from here to here, then if I double it, which is 40 feet, I in fact have the width of that rectangle. So this yellow portion, the rectangle, at least I can find the area of that. So let's do that. And we get that the area is length times width, which we now know. Substituting and multiplying, we get 2,400 square feet. But we still have to account for the end half circle, called a semicircle. In this case, finding the area of a circle, which you recall was pi r squared, but now recall we only want half the circle, so we'll take half of it and substitute in what we know. We get this, which worked out gives us 628 square feet rounded to the nearest whole square foot. See, there's where my square foot came from. But now we can simply visually see the area of the entire field is simply the sum of the area of the semicircle and the rectangle. And see, as we add them, they are like units, square feet, so we have permission to add. And the area of our field is 3,028 square feet. 3,028 square feet for the entire field. So in this case, what we had to do was take a more complicated figure and visually on scratch paper break it into pieces which use our fundamental formulas. Now sometimes rather than adding two areas, we have to subtract. Now you see, if we wanted to find the area of this sort of circular track, we could find the area of the entire big circle, then subtract the little circle out, and we have what's left. So the area of the big circle is found by substituting into the formula pi r squared, and working that out on a calculator. In this case, we get 452.389 square meters, and we want it to the nearest tenth of a square meter. Now, nearest tenth is here. Notice, since I'm using 4 digits and possibly 5 to find out how to round off, our pi should at least be that many digits of accuracy. So there's 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Now let's keep it one extra digit until we're finished with our arithmetic. So we get 452.39. One more digit than is being asked for. That's perhaps a safe measure in your computation with calculators where you're doing sub-steps. Always keep at least one more digit or place than asked for, and then round. Here we have it. Pi times the radius squared. And of course, squaring the meters is going to give us meter squared. Squaring this on a calculator first, then times that, we get 120.76 square meters. And see, as with our big circle, we have kept one extra place. Now, the relationship between the small circle and the big circle is we wish to subtract the small circle to find the area of the remaining track. So we wish to subtract the small circle area from the big circle, and doing that we get 331.63 square meters. Now see, we've kept one extra place, but we wanted originally to have it accurate to the nearest square meter, tenth of a square meter. So we'll round this to the nearest tenth. That's less than 4, so we drop it. So our track, in this case, is 331.6 square meters of area. Now see, in the previous problem we had to add 2 areas, in this case subtract. There now, isn't that a juicy one? But to a draftsman, particularly a pattern maker or a sheet metal worker, that's not at all unusual. In fact, that's fairly simple. So your task is simply this. On scratch paper, find a sub-area that you can start with. There are several places you can, perhaps with this quarter of a circle there. You might decide, let's find the area of this circle and divide by 4, since that's only a quarter of a circle. And doing that, you get this, pi times the radius squared, and we're going to divide by 4 to get a quarter circle. Now, following through and doing that, we would get this, and since they want the area to the nearest whole square foot, I'll take at least one more place than needed. And since that will require that I need 1, 2, 3, 4 digits at least, I'll keep pi to 1, 2, 3, 4 at least. I took 5. So now we have the quarter circle. Now what's next? Perhaps to add in that area of that small triangle. We can see that its base is 8 foot, and since that's a right angle there, we can see that its altitude is the same as the radius, or 12 foot. And that's easy. So quickly, the area was 1/2 base times height. There's a base times a height. That's 4 times 12 is 48 square feet. So that part was easy. So what next? Well, there's a rectangle, and we certainly have its height. If we were to take that plus that, which is a radius, plus that, which is another radius, plus that, we have the length, which is 20 feet. That plus 6.3 here, 6.3 here, plus 3.4. Sometimes in a composite figure like this, you can double check. Notice that this radius of 12 feet is 12 feet also across here. So I have 12 feet plus 8 feet, which is also 20. That's not only faster than what we did, but it gives us a cross check. If I find the area of this rectangle, it's going to be too much, so I know ahead of time I'm going to have to subtract the semicircle out. But first, the area of the rectangle, length times width, which is so simple, we can probably do that mentally. And we have its area, 148.0 square feet. So that 0.0 tells me that that's actually an accurate calculation. It actually really is 0. It's not rounded off. Now what does that leave us? We must now find the area of this half circle so that we can subtract it. And so we have the area of the circle on top, then divided by 2 because we want only a half circle, and we have the area in square feet rounded to one more place than I want in the end. So now we have all 4 of my sub-areas, quarter circle, triangle, and rectangle, which I'll add. Then I will subtract the area of the semicircle. There, the area of my top quarter circle, the triangle, and the rectangle added gives me their sum. Now taking that lower half circle and subtracting, we get our final in total area. Actually, if you do this very much as a draftsman or an engineer, you can do it all on the calculator without ever touching the paper except to look at your figure as you subdivide it. But that's purely a matter of experience more than teaching. Now, of course, the examples can go on, as they will in your lesson, but the principle is the same. You're going to either subdivide it and add pieces or subtract pieces. And that's a matter of cleverness and your ability to sketch what you have. Let's work that last problem. Let's say that this is a sketch of the track like you see at most high schools or colleges. And you have to coat it with cinders, and before you order your cinders, you need to know what's the area of that track. When you look at a figure like this, the first thing you try to do is to break it down into a series of rectangles and or circles or triangles being added and or subtracted. So perhaps the first thing we notice about this particular figure is that one of its straightaway stretches is a rectangle that's 300 feet long by 15 feet wide. And furthermore, I have either two of them, so I can find the area of this strip and double it, or I might just well double it while I'm here. If this is 15, then if I'm going to double it, it's going to be 30. So I have a 30 by 300. So the area of a rectangle is the width, which is 30 for the two of them together, times the length, which is 300, and that gives me 9,000 square feet for the two of them together. Looking at the ends, we can see that this is two halves of a circle with the other half over here. So in our mind, we just sort of slide those together, and the outer one we see is a circle with a radius, because we do need to know that radius since the area of a circle is pi times the radius squared. So the radius is the distance from here to here, so we have to realize that the radius is in fact half of the distance clear across, and the distance clear across is 200 feet, so the radius in fact is going to be 100 foot squared. And of course squaring the feet gives me feet squared, and 100 is easy enough to square mentally, isn't it? There's 100 times another 100 times pi, and if we have memorized our pi, 3.1416, let's say, to that much accuracy, and we want to multiply by 10,000, there is 10, 100,000, 10,000. So the area of the larger circle is roughly 31,000 square feet. But from that, we must subtract the area of the inside circle. So from our sketch, can we determine what its radius will be? That is this radius right here. Well, if the total distance is 100, which we determine by taking half of this, and the distance across this track is 15, then this distance will be 85 feet. So to find the area of that inside circle, again we have the formula. Area is pi times radius squared, and pi we either have on our calculator or we have memorized. The radius is now 85 feet squared, and of course squaring the feet is feet squared. So from our last lesson, do you remember the fast sequence for doing this on the calculator, the 85 squared? You're going to take 85 times equal, and that will square it, or you will find an x squared key and simply hit 85 in that one key. So doing this way, there's 85 times equal, and that's the square, then times pi, and if you didn't have pi in your calculator, you'd have to enter it. 3.1415926, as much as you need, then equal, and let's round this off to the nearest whole number, which would be 22,980. Whoops, did you catch that? We had read the calculator wrong. That's 22,698 square feet. Recall that when you're using a calculator, it's very easy to misread or punch buttons. So always when you're using the calculator, do all of your work twice on the calculator and check it twice, because this miswriting is a very common error even among the experts. Now, let's see what we have. We have the area of the inside circle, and we also had the area of the outside circle, and if we subtract the two, we will get the area of the ring, or the end of the track, the two ends actually, which is 8718 square feet. And recognize that we kept the square feet to remind ourselves we can only add square feet to square feet because these are measurement numbers. Now to these two ends, we want to add the two straight stretches, which was 9,000 square feet. Adding those, we would get 17,718 square feet is the area of the track. And so our problem has been accomplished by breaking the original track into recognizable units. Two rectangles being added, and then two circles which are split apart, but two circles with the inner one being subtracted from the outer one. Let's say after you were done, you call up your cinder company to order the cinders for this particular track, and you told them that the area of the track is 17,718 square feet, and the question was, how many square yards is that? Because we sell this material in yards. So now you have another problem, a conversion of units problem from square feet to square yards. So now we have a chance to use what we learned 2 lessons ago. But you might be in a position where if you try to find a relationship between square feet and square yards, it might not be listed. But you do know that 3 feet is 1 yard. So let's simply think our way through this. What is a square yard? Well, it's an area that is 1 yard by 1 yard, a square area. But we also know from this or from memory that a square yard is 3 feet. And we can see that 3 feet by 3 feet will give me 9 square feet. But that's just another way of describing this 1 square yard. So we were able to figure out for ourselves, knowing what areas really are now, the conversion of units that we need. We now know that 9 square feet is 1 square yard. So setting our problem up for conversion of units, first creating a fraction out of it, we recall that I need a square feet on the bottom if I'm going to cancel that one on top. So I try to find a relationship that has square feet as half of it, put that on the bottom. Now I can see these are going to cancel, but I need an equal amount on top to ensure that I'm going to be multiplying by 1, because anything divided by itself is equal to 1. So that tells me put an equal amount on top. Do you recall this from 2 lessons ago? Now the square feet cancel out, leaves me with square yards, which is what I wanted. So now I simply do as the indicated arithmetic is given to me. 17,718. This dash means divided by, so divided by 9. So I'm going to divide this by 9, and doing that, I get 1,969 square yards. Have you ever had a problem similar to this, not from a high school track, but from a driveway or a sidewalk? They're the same type of problem. The only thing that's different is the components of the shape. Just as frequently, the areas that you want will not be spread out flat on the ground or a piece of paper, but is wrapped around some solid. Here we have a rectangular solid shaped like a shoebox, if you would, and we want the surface area. That is, how many square meters in this case of materials is used all the way around this solid. Do you recognize all of the rectangles we need? There is this length, the end of the box, and we recognize that just on the opposite side of it is another one exactly the same size. So that will give us 2 pieces to this box, but also we have the end and the one opposite it will be exactly the same size. And then, of course, finally, the top and the bottom. So essentially we have 3 parts: the side, the end, and the top, and then we'll double it to get the other 2 sides and the bottom. So let's figure this side first. It's a rectangle, even though it's drawn in perspective. So the area of a rectangle is 3 by 7, which is 21 square meters in this case. The area of the end is 4 by 3, which is 12 square meters. Then the area of the bottom is 4 by 7, or 28 square meters. Then adding those, we get 61 square meters is the side, end, and bottom. But then to get the other half of our box, we have to double our results, which give us 122 square meters of material. The material was used to construct the outer surface of this rectangular solid. So you see, this is not unlike the problems that we just did. It's that we have to begin to think in terms of 3 dimensions, and sometimes that takes just a little bit of extra effort in visualizations. For instance, on this one, can you visualize all the components of this? Sort of shaped like an oatmeal box, if you would. Well, we can see that we have a bottom and a top, which are of equal area. So if we could find the area of one of them, we would double it, and at least we found the surface area of top and bottom. Well, while we're thinking of that, let's do it. That top is a circle, and the area formula for a circle is pi r squared. The radius is 4 inches, and we can square that mentally, so that's 16 square inches. 16 square inches. Multiplying these two using pi to however much accuracy I need to get, let's say, accurate to the nearest 1/10 of a square inch. And we have that the top is roughly 50.3 square inches. And all we need to do is to double that, and we have top and bottom together. Now how about the side, that piece of cardboard that wraps around? At first that seems like that might be a bit tricky, but it really isn't if you begin to think about it in the right way. Consider this, if I were to cut the side of this and then take that paper wrapped around this box, if we want to think of it that way, and unwrap it, what you would have is a sheet of paper that is essentially a rectangle. It's just that it's wrapped around the box. And furthermore, it's 18 inches wide here, which is the height here. And you can see that the length of this sheet that wrapped around this cylinder is the same as the distance around the cylinder, which several lessons ago we learned to call the circumference. And the circumference was pi times the diameter. And of course we know what pi is, and the diameter is twice the radius, or 8. So we have a rectangle, and the area of a rectangle is length times the width, and the length is my pi times 8, and my width is 18. Now note, my length is inch. My width will also be in inch. So if I multiply those, I will get square inches, which tells me I am dealing with area. Then doing this bit on the calculator, we get the area of this rectangle, which is the area around what we call the lateral surface of this circular cylinder. So using that, along with the areas of the top, we get the grand total of all of the surface areas, which would be 553 square inches. So sometimes you have to think regarding a solid figure, what would happen if you peeled this side off? Pretend as though it's paper and that you could cut it and peel it off and stretch it out. In your mind, if you did that, what would it become? And very frequently it'll be a rectangle or a triangle. And of course those are my component pieces, the rectangle and the two circles being added. Can you see how this type problem would be very, very common and frequent in all forms of drafting, architecture, and engineering? After a while, you just think in terms of geometric figures and formulas if you pursue your education not too much further. This is your host, Bob Fennell. Good luck.